Okay, this is lesson 2.3, elements and compounds. And then the first question is, why does burned toast taste so bad? I guess that's a matter of preference. Some people may like it that way. Um, Bread on its own tastes different than when you do a nice toast it. And then when you burn it, obviously, it makes a big difference. So even though it's nice to have toast for breakfast, you have to make sure you don't cook it too long. How are elements and compounds different? Let's talk about these things first. An element is the simplest form of matter that has a unique set of properties. Okay, examples that you've probably talked about before: oxygen, hydrogen are two known examples. Anything on the periodic table is considered an element in its simple, and so that's just matter in its simplest form. It's just that one thing. A compound is when you take these elements and you combine them chemically, and you make something new. And usually, when you combine them in a proportion. Like, for example, water is H2O, 2 hydrogen, 1 oxygen. But a compound is when elements chemically combine. Carbon, oxygen, and hydrogen are chemically combined in sucrose, which is just simple sugar. In every sample of sucrose, there are twice as many hydrogen as oxygen. This proportion is fixed. All samples of sucrose have that, all right, have twice as much hydrogen as oxygen. Now, there is a key difference between elements and compounds, and this is a big key point, if you will, because there's a key here. Compounds can be broken down into simpler substances by chemical means. So we can take a compound and we can break it apart into its elements, but elements themselves cannot be broken down. Elements are the simplest form of matter. Big difference between compounds and elements. How to break down compounds. Physical methods that are used to separate mixtures cannot be used to break compounds into simpler substances. So, for example, if you boil water, you're not breaking it apart into oxygen and hydrogen. All you're doing is making it change state. You're going from liquid water to water that's a vapor, right, to gas. So the amount of oxygen and hydrogen is still mixed together. Okay, they're not separating when you boil water. When you dissolve sugar in water, okay, you still have sugar. You're not breaking it apart into oxygen, carbon, and hydrogen. Okay, it does not mean you can't break it down in other ways. It's just that in the case here, you're not breaking it down. So when you dissolve sugar in water, you're not breaking it down into its separate parts. Before you can break these compounds down into elements, you must have a chemical change. Okay. So a chemical change is a change that produces matter with a different composition than what you originally had. So you're making something entirely new, all right, when you have a chemical change. So here's an example of sugar heating. I wouldn't necessarily say you should do this at home because you'll ruin the pan. But if you take sugar and you heat it, you see it starts to caramelize here, and then it really burns when you get it down into solid carbon. This still has a little bit of sweet flavor. This is awful, right? But this breaks the sugar down into its substance, carbon, and then you get water vapor where the hydrogen and oxygen disappear out of the sucrose. So that is a chemical change, and that helps you take things apart. So going back to our burnt bread, what do you think happens to the compounds in bread when it is overcooked that causes the change in the taste of the bread? And obviously, it's a chemical change that changes the taste of the bread. They're broken down into solid carbon, so the components of the bread, instead of being all the mixture that made the bread, is now broken down into solid carbon, which is not good to eat. Can the substances that are produced when sugar is broken down when heated also be broken down? Once you get carbon out of that sugar when you heat it on the stove top, understand that you cannot break carbon down into simpler substances. Carbon is, of course, an element, and you know that from what you know from the periodic table. Another way to break down a substance into its components as a chemical change is water. You can run electricity through water. So if you run water through electricity, you can break it down into hydrogen and oxygen, and hopefully that we'll get an opportunity to do that when we go into lab at some point. So chemical changes will break things down. Sugar can break down into carbon and water, and you can take water by using electricity to make hydrogen and oxygen. In general, the properties of compounds are quite different from those of their component elements. Obviously, sugar, sweet tasting, nice to put into your coffee if you like that. But carbon, black solid, tasteless, probably kind of, I don't know if we can describe it, but it'd be like chalky. Definitely something you don't want to ingest. Hydrogen, when on its own, will burn when you put it in oxygen. But then when you have it as water, it actually puts out fires. So if you have hydrogen alone and you put it in a flame, it will light the flame up. But if you take the hydrogen when it's mixed with oxygen to make water as a compound, it will put a fire out. So compounds and elements on their own don't necessarily have the same properties. Sodium and chlorine. This is another good one. When sodium and chlorine combine to make salt, sodium chloride, there's a change in composition. So here's sodium by itself, soft gray metal. Chlorine on its own is a pale yellow gas. In fact, chlorine gas on its own is poisonous. If you ever hear about chlorine gas leaking in an area, it's poisonous and they have to evacuate because chlorine gas is not good for you. So we're taking a metal and a poisonous gas, and when they combine chemically in a 1-to-1 ratio, you get table salt, which is something that we put on food to provide taste. So two things on their own that necessarily aren't good for us to ingest, when you combine them chemically, make something that we do ingest and do eat. Couple questions to review. Can elements be broken down by chemical changes? Can compounds? And obviously the answer is no. You cannot break down elements into simpler substances. Compounds, though, can by chemical changes. And that's it. Again, that's the main difference between elements and compounds. How can substances and mixtures be distinguished? So we're talking about elements, compounds, and mixtures. So deciding whether a sample of matter is a substance or a mixture is based on their appearances can be difficult. Sometimes you have to run tests. I mean, if you look at a homogeneous mixture, it looks like it's only one kind of matter, like it's only one thing, when in fact it could be more than one thing, especially if you tried to separate it. You can buy different types of milk, let's say, whole milk, low fat, no fat, light cream, heavy cream. And you can conclude that milk and cream are mixtures. So you might infer that these mixtures that differ in the amount of fat they contain. So milk on its own is not a pure substance. Milk is a mixture. It's a mixture of milk and the fat that's inside. So differences in types of milk mean that milk is a mixture. Gasoline, once you start driving, and some of you might be driving now, I'm not sure, but when you buy your gas, the gases that you buy, some are more expensive than others, and that's because of the octane ratings, right? And again, the mixture of the gasoline can vary, and that's what difference in the cost is. So gasoline, because there's different types, must be a mixture. So key point, if the composition of a material is fixed, the material is a substance. If the composition of the material may vary, the material is a mixture. And there's the word may vary, okay? We assume that it could vary, right? But when we know it's fixed, it's definitely a substance. It's definitely an element or a compound. So here's a little flow chart. You may want to screenshot this or write this one down, pause and write this down, because this is a good way to determine differences, okay? So you have matter. So the first thing you look at, is it a substance or is it a mixture? If a mixture can be physically separated into substances, okay? Substances can be elements or compounds, and a compound can be chemically separated to be an element. But mixtures can be two types, homogeneous or heterogeneous. Heterogeneous, you can see the separate parts. Homogeneous, you can't, also known as a solution. And this is a nice little chart that breaks matter up into its, I want to say 4 components: elements, compounds, homogeneous mixtures, and heterogeneous mixtures. No matter what you do to a silvery liquid, it doesn't seem to change. Is it more likely to be a substance or a mixture? And again, this is going to be based on what you observe, but no matter what you do, if it doesn't seem to change, I would assume it is a substance, okay? If it was a mixture, you might have been able to separate it when you did some things to it. But if you have a substance that you cannot separate or see if there's different parts to, make the assumption that it is a substance. Now, if it's an element or compound, you're not sure until you run some more tests. What do chemists use to represent elements and compounds? Chemists use chemical symbols, all right, to represent elements, and chemical formulas to represent compounds. And this is something we're going to spend quite a bit of time on this semester. So using symbols was started with the alchemist, and John Dalton was one that used drawings to represent chemical elements. And you can see this is what alchemy said: lead, tin, zinc. Dalton came up with symbols also. So we use symbols to represent elements for a long time. Today, the symbols were based on a system developed by, I always butcher this guy's name, Berzelius. And he based his symbols on Latin names. And from that, he came up with chemical symbols. First letters of chemical symbols are capitalized, while the second letter is lowercase. And those are the symbols that we see on the periodic table today. If the English name and the Latin name of an element are similar, the symbol will appear to have been derived from the English name. Ca for calcium, N for nitrogen, S for sulfur. Okay. And you can see some of the Latin names. So sodium is Na because its Latin name is natrium. Potassium, K, kalium, and so forth. And these are just some examples where the name that we use doesn't match the symbol, but it's because of the Latin name. All right. And again, this is just some examples. Chemical symbols provide a shorthand way. So let's say H is hydrogen, O is oxygen, C is carbon. Water, H2O, 2 hydrogen, 1 oxygen. Sucrose, which we were talking about, is table sugar, C12H22O11. And you can see that we have 12 carbons, 22 hydrogens, 11 oxygens. Imagine if we didn't have shorthand way and we had to write the names out. That would make formulas very difficult to follow. So subscripts. This little 2 after the H indicates that we have 2 H's. So the subscripts always follow the element they apply to. If you don't see a subscript, then it's just an implied 1. So in this case, we have 2 hydrogen, no subscript, 1 oxygen. And we know that H2O is always going to be water because it has to have a fixed composition to be a compound. Chemical symbols are abbreviations for the names of elements in what language? Latin. It comes from Latin. And that was the language that was spoken by people in Europe at that time. And that was a common language. Quickly, why is a periodic table useful? A periodic table is an arrangement of elements and where the elements are separated into groups based on properties. The periodic table allows you to easily compare the properties of one element to another element, so one group to another. So as we look at the periodic table, as we go up and down, these are groups, okay? And we'll do some stuff with the periodic table later on to really delve into the groups, but you can see that there's symbols in each square, and that tells us the elements that we're talking about instead of writing out the names. They're listed in order from left to right, top to bottom, by their atomic number, which is unique to each element. The atomic number is usually the big number you see right above the symbol. Hydrogen, top left. Helium is top right. And then lithium is right below hydrogen. It's the left end of the second row, and then it starts to go across 4, 5, 6, etc. Each horizontal row is what we call a period. There are 7 periods. The number of elements per period ranges from 2 in period 1 all the way to 32, which we find in period 6. And again, we'll describe these a little bit more in detail later on. Within a period, the properties of elements vary. So as you go across the periodic table, the properties vary. But there is a pattern to it. In a group or family, they have similar. So that we're talking about vertical columns. Each group is identified by a number and the letter A or B. So 2A, beryllium, magnesium, calcium, strontium, barium, radium, and we can work our way to 3A, etc. But groups have similar properties, while periods do not. Okay, which elements are included in the periodic table? Every single one that we know of, and even ones that we just make in lab that don't necessarily find them in nature, but they are elements that we have produced.